Let's take a look at a simply supported beam with a concentrated load acting in the center of P at L on 2. And we know that this would be 1/2 of P and 1/2 of P because of the symmetry in this problem. And our goal here is to try to determine the amount of deflection in this beam, y, at any given point. And again, here this is greatly exaggerated, of course. Now, one way to do that would be to try to calculate or estimate the radius of curvature at any given point. And recall from our discussions on bending that the radius of curvature is EI, the flexural rigidity, over M. And for this beam over here, we can make a cut at a distance of x, and we could calculate the moment at the cut as 1/2 P times x, and that's in response to this torque being generated. So let's plug that into here for M. So we'll get 2EI over Px, where all of these are constants. So it's an inverse relationship with x. For example, back here at x equal to 0, rho would be infinity. And recall, for an infinite radius of curvature, that's flat. Which tells us that right here, this is basically flat. And as x increases, rho decreases, which tells us that the radius of curvature gets tighter as we work our way along, reaching a minimum someplace underneath P. And then by symmetry, it would go back up and be flat on the other side. So we find that the radius of curvature gives us at least a hint, the shape of this curve. So let's define y as a deflection. And it's at any given point here. So there's y. Y prime then, which is dy dx, will be the slope at any given point, and y double prime would be the concavity. In general, for a rigid beam, we can see that y would be fairly small in comparison to the length of the beam. We would anticipate the slope to be very small. Using calculus, we can determine the radius of curvature. Rho is 1 plus y prime squared to the 3/2 power over y double prime. And y prime here is fairly small, and we're squaring it, which is going to make it even smaller. So this value here is going to be very tiny compared to 1. So we can say that it's basically 0. And as such, we have 1 to the 3/2 power, which all of this will just become 1. So we find that for beams, radius of curvature is basically 1 over y double prime, the concavity. But up here, we've also shown that this could be EI over M. With this, we can develop a very useful equation, and that is that y double prime is M as a function of x over EI. Let's see what we can do with that. Here we have a simply supported beam with a concentrated load P acting in the middle at L on 2 from each end. We know from symmetry that the loads here would be 1/2 P and 1/2 P on each side. And when dealing with this moment equation over here, I like to move the EI to the other side. it'll make it easier to set it up and to do the integrating on this side that we're going to have to do. So step 1 is solve for a moment as a function of x. And if we look at this, we have two regions, region 1 and then region 2. So what we'll do is we'll start with region 1, and if we come out here some distance x and make a cut here, these will be our cuts, right? We have 1/2 p acting up at a distance of x away, so the moment here would be 1/2 p x. So with that we can start. So for the region of 0, less than equal to x, less than equal to L on 2, which really just is domain 1 here, we can say that EI, y double prime, is m as a function of x, which we found to be 1/2 px. And now we'll integrate both sides of this, and we'll get EI y prime as px squared on 2 times 2 is 4 plus c1, and we'll integrate it again to get px cubed on 4 times 3 will be 12, c1x plus c2. This represents the slope, which is a function of x, and this represents the deflection, which is also a function of x times EI. If we can figure out these constants of integration, we'll have the functions that will describe these. So step 3 here is to find the integrating constants. We know here at x equal to 0, y was equal to 0. So we'll plug that in, and we have y is 0, x is 0, x is 0, and we quickly can see that c2 is equal to 0. So c2 is 0. To get c1's a little trickier. We can't use the other logical boundary condition of x equal to L, y is equal to 0. That's back here, because this equation set is not valid in that domain, so we can't look over here yet. We also don't really know the value of the slope anywhere. Now we could hypothesize that the slope goes to 0 directly in the center, and in this case it probably does, but we shouldn't make that guess, and if the load had been an offset load P, that would not be true, and we'd have to find that. So let me continue by not assuming we know the slope anywhere to see how we would solve this. In order to use the boundary conditions that are on the right half side of the beam, we need to develop and follow the same 3 steps for the right half of the beam. So this would be L on 2, less than equal to x, less than equal to L. If we take a look at our beam, we're going to make this cut in region 2. So x now reaches all the way out to here. And the distance from the cut to this load P would be x minus L on 2. And with that, we can develop our M equation. So M2 will be, we're fighting with this 1/2 P still, so we get 1/2 Px. And this is common. We often pick up the same portion of the moment that we had in region 1 because we're still fighting with it all the way across the beam. Minus, right, this is negative because we're going to have a moment in that direction to offset that. So minus P, and the distance to P is x minus L on 2. And when we do this, leave it in that form. You'll see later that that's very easy to work with. And we know then, according to our relationship up here, that that is EI y2 double prime. So integrating it, we'll get EI y prime px squared on 4, same as the earlier term, minus p, and we can treat this as one larger variable. So we have x minus L on 2 squared over 2 times the derivative of what's inside, which is just 1, plus C3, another constant of integration. And integrating it again, we'll finally get our deflection function as px cubed on 12 minus px minus L on 2 cubed over 6 plus C3x plus C4. And now we have a new set of boundary conditions that we can apply to this half of the beam. The most useful one would be that at x equal to L, y is equal to 0, but we still have two unknowns in this equation. So that wouldn't give us any conclusive answer, and we don't know much about the slope yet as well. So right now we don't have any useful boundary conditions to apply, but we do have another criteria. And the other criteria has to do with what we call the continuity or patch conditions. And the idea here is right at this boundary of where x is equal to L on 2, both of these families of equations have to agree with each other. They have domains that overlap here at this one location. So we find that y1 should equal y2 at that location. And this makes sense. Y represents the deflection of the beam at that spot. If y1 didn't equal to 2, that would imply that the beam was broken. So we know that that should not happen. And we could also say that y prime 1 should equal y2 prime, and that's slopes. So the slopes should also merge and agree with each other at this spot down here. And in order for them not to agree, it would have to look something like this. And again, that would be a problem for our beam. So the continuity or patch equations allow us to relate this family of equations over here with these at specifically that boundary x equal to L on 2. Let's start with the slope conditions. So y1 prime should equal y2 prime at x equal to L on 2, which tells us this function here should equal this function here. Now some very nice things are going to happen when we look at this. If I bring these down to here, we find that for any x value that we plug in, we have a counter value to it on the other side, and these will subtract out. So if we plug in our x equal to L on 2, which we don't need to do, we can see that these will both drop out. If we plug in L on 2 inside of here, we find that this goes to 0. And this will generally happen if we leave the moment equation in that form. The term inside of here will represent that boundary as we cross into it. And from here we can very easily see that C1 is equal to C3. The next continuity event we would look at is that y1 should equal y2 at x equal to L on 2. And here we have y1. Over here we have y2. So we find that this term will cancel with that term. This term will go to 0 when we plug in that limit. C1 equals C3, and this term will cancel with that term. And we find that C4 is equal to 0. We could see that C2 equals C4, and that's why there's 0. Now we can apply our boundary condition, which is that at x equal to L, y was once again 0. We're back here at this support, and therefore the beam can't deflect there. Now this one will be the most algebraically intensive. This is 0, but these are not. So we'll get 0 is p L cubed on 12 minus p L minus L on 2 cubed over 6 plus C3L has to equal 0. This term in here becomes L on 2 cubed, which will give us PL cubed over 12 minus PL cubed on 8 times 6 will be 48 plus C3L equal to 0. We can run through here with one of the L's, making that a squared and a squared. Looking at this, both terms have a PL squared in it, so this would be 4 over 48 minus 1 over 48. So this becomes 3 over 48 PL squared plus C3 equal to 0. And that's 1/16, and we find that C3 will be negative 1/16 PL squared, and it also is equal to C1 by our boundary conditions. So with that, we finally have chased down our value for C1 over here, as well as here. Now, from the symmetry of this event, these equations really do relate to each other well as if you're working in from either end. From here, we'll get our solution as EIY as a function of x is px cubed on 12 minus PL squared over 16x. And that's the deflection at any location from 0 to L on 2. This will also give us our equation for slope as px squared on 4 minus PL squared over 16, which we could also get by just quickly taking the derivative of this as well. Now, originally we had thought that possibly the slope would be 0 at L on 2. And it's probably likely that it is, but now we can verify that. So we could ask, when is the slope 0, which would represent a max min for y. Take the derivative, set it equal to 0. So we get px squared over 4 will equal PL squared over 16. And we see that it's not a function of the load itself. So we get x squared is equal to L squared over 4. Taking the square root of both sides, we'll get L on 2, which our guess was correct. We can also then solve for y max, which will occur at x equal to L on 2. PL cubed over 8 times 12 will be 96 minus PL cubed, if we bring in the x equal to L on 2, over 32, of which if we multiply and divide this by 3, we'll have a common denominator of 96. And this reduces to negative 2 over 96 PL cubed. And I should put my EI back in here too. We still have that. So our final solution is that y max will be negative PL cubed over 48 EI. And that occurs at x equal to L on 2, right in the center of the beam. And generally this is the formula that we would want, because most codes require that the deflection, y, be less than or equal to some length of the beam over 240. That's a general form, although you could see L over 360 for ceilings and floors that you don't want to vibrate or maybe have plaster on them. It could be as high as L over 120 for non-habitable spaces or basements, things like that. Now, fortunately, we don't have to do this ourselves for every single beam. This is an example of how the equations are developed. The equations for deflection and slope for the most common types of beams have already been worked out, and they're listed in tables. Here's an excerpt of one of these. And the first thing to check is to make sure that you're working with the correct form of this. So this has a concentrated load acting in the center of a simply supported beam. And over here, the maximum deflection in the center is PL cubed on 48 EI, which is what we have. Now this negative here is often omitted The negative's there to indicate that it's a downward acting deflection. Recall most of our equations we work with y being up as positive. So it's just telling us that it's down. And most of the time we'll know that, so it's often written as an absolute value. And we also have over here the deflection at any location less than L on 2, and that will agree with what we've got right here if we clean it up and factor it out a little bit. This can also be interesting. The slope at specific locations. Right now we know the slope at the center is 0, but we might want to solve for the slope at x equal to 0, the starting point. So at x equal to 0, y prime will be 1 over EI. That goes to 0, and we get PL squared on 16. So there's our PL squared on 16 EI, which is slope. And generally, if we wanted that as a numeric value, we could set it equal to the tan of theta. However, these angles are going to be very small, so this will generally just be equal to theta itself in radians. And you'll find out later that that's also quite a useful term to have. Fortunately, these tables do save us a lot of time, but we do have to understand how to use them. And it's also good to be able to do this process if you run across a load configuration that's not listed in one of the tables. So the general format to follow is solve for mx in your region, integrate it twice, and then chase down the constants both with boundary conditions and with patch conditions. And obviously, if you have a beam that has a lot of different loads on it, this can be a lot of work. You could have 3 or 4 domains with up to 8 constants of integration, where you're chasing down all these different patch values. In summary, we're trying to find the deflection y, which we would call the elastic curve of the beam, and we define EIY as EI times deflection. And we go in the reverse direction here. We can take the derivative of this, EIY prime, which will be EI theta, which is the slope at any location along the beam. If we take the derivative again, we get EI y double prime is the moment as a function of x. And recall when we were doing V and M diagrams that V was defined as dm dx, which tells us if we take the derivative of the moment equation, we'll get V as a function of x, which is the shear at any point along the beam. And also recall from our V and M discussions that the distributed load curve was equal to negative dV dx. So taking the derivative one more time, EI y to the 4th derivative, we would get negative W as a function of x, which is the distributed load value. And it's rare that we see so many sequential derivative values that all make sense and have meanings that we can understand. In physics, you might recall seeing x as location, and we get a derivative of location as dx dt, or x dot, and that was speed. We could take the derivative again, x double dot, we know that was acceleration. We could keep going with this. We could take the 3rd derivative of location, and you get something called jerk, but doesn't really have a lot of meaning. It's the rate of change of the acceleration over time. It definitely imparts a lot of forces onto equipment, and it's something that should be minimized. X to the 4th would be snap, then crackle, and then pop if you want to keep going on and on and on. But these all have lost meaning for us. We understand location, speed, and acceleration, but not necessarily those. Interestingly here, though, we have the deflection y, followed by the slope, followed by the moment, the shear, and then ultimately the distributed load value that started it all. And every one of those values makes sense. Going the other direction, if we know the equation for the distributed load, we could integrate that, and that would give us V. We could integrate that, that would give us M. Integrate it again, we would be able to get theta, and integrate it one last time, and we would finally get our equation for deflection. So the distributed load starts it all, and by sequential integrations and a lot of constants of integration along the way, we can directly derive the elastic curve. Generally, the process is to start with the moment equation, which is fairly easy to define, and it minimizes the number of constants that we have to chase down. Thanks for watching.